Yeah, thanks. So like you mentioned, I'm a data scientist at Endgame. Endgame's a security company. We've been working to try and use data science to solve security problems. Over the past couple of years, we've been a federal contractor, and we're moving into making our first enterprise product just recently. So I'm putting the punchline right up front. I hope to convince you of these things over the course of the talk. Python tools that have been built for text classification can easily be adopted for malware classification. And when using instruction engrams, your disassembler and analysis passes are very important. And I'm going to talk about a bunch of different projects. You can go to this URL. It just points to a gist I have on GitHub that has links to all the projects and things I talk about if you just want to go right to the project web pages and not have to Google everything. There was a data science competition that was hosted recently on the website kaggle.com. Microsoft made available some samples of labeled malware and asked the question, what family of malware did all these samples belong to? So there is a problem out there that, when you're given an unknown binary, is this malware or not? And you can build a classifier for that, but this competition was more focused on now that you know it's malware, what kind is it? And answering this sort of question is useful for knowing code reuse and knowing how different families evolve over time. Once we have a good understanding of that, it's going to make it easier for us to detect it in the future. So I use this competition to kind of learn about what features and how this can be done in the security industry. This is some details about the data. There were about 20,000 samples. It was about half a terabyte uncompressed. There were 9 classes, and here's the relative frequency of all of those classes of malware in the training set. So for each sample, we had two files associated with them. The first was a hex dump of the raw binary data, and here you can see in this text file, there's just an offset, and then that tells you how far into the binary file you are, and then what binary data was there in hex. And so the whole binary data wasn't included. All of these samples were portable executable files, and all those files have PE headers, what are called PE headers, and all of those were stripped. And I think the purpose of doing that was so that it was harder for us to run the malware, not only to infect our computers or do something wrong or mess up, but also to so that we focused on static analysis of these binaries instead of running them in a controlled environment and to see what they did. That's that's something else you can do. It's called dynamic analysis, but I think it wasn't the focus of this competition. So that's one file we were given for each sample, and the other was the disassembly file. So this is the raw text dump of the output of a program called IDA Pro, and that's the interactive disassembler there. It's pretty much the leading disassembler on the market. It's commercial, it's restrictively licensed, and it's also very good at what it does. So the IDA Pro is meant to be kind of run interactively by a reverse engineer, and that reverse engineer is meant to unwrap parts of code and find out what it's doing and relate it to other parts of code, and this tool is excellent for that. In this case, in this competition, the IDA Pro was just run in batch, and it just dumped the output to text, and we were handed that text and asked, well, what could we do with it? So this is the header of one of those text files. You can see, again, there's offsets, and in that first column, we also have section names. And then using those offsets, we can determine how, yeah, that's why I have multiple possibilities. Where did that go? Oh, okay. Yeah, so where was I? Section names. So you can see what sections, each PE file has a certain number of sections, and you can see those here in this disassembly file. Here are the top occurring section names, and good reverse engineers will probably recognize those common section names. So scrolling farther down in this example disassembly file, we get to the .text section, which is usually where the executable code is, instructions. And so you can see what IDA Pro thought of this. Again, the offsets are on the left, and the raw binary data in hex is just next to that. But then on the right, IDA Pro shows you what it believes those raw bytes are. And these are instructions in assembly. So I used those instructions, what is on the left, the push, move, XOR, etc., in my features, and I'll describe that later, but I also just kind of threw away the operation string. So here again, the top occurring instructions in this data set. Move appears a lot because you need to move arguments onto the stack before calling each function. And you do that once for each argument, so it turns out that there's a lot of moves. Scrolling farther down in this example disassembly file, we get to the IData section, and this shows you what common Windows libraries are being imported by this sample and what imported functions they're using there. So what can we do with all this data? This is kind of a data flow schematic of what my solution was, and then I'll go into detail about how I implemented each of these boxes in these coming slides. So WhiteEngrams. This is a feature you can use to classify malware binaries. You can really, on a low level, you could really just count up what bytes occur in the file. There are 256 possibilities, and then you just count up how many there are. You'll end up with an array that's that long, and you can feed that into any classification algorithm. If you want to get a little bit more complicated, you can count how often one byte follows another for 2 grams, and you can go up to 3 gram, 4 gram. I think people in this competition at some point looked at entire lines. But when you're doing that, your space of possibilities, your space of features is very, very large, even if it is sparse. So you can't really fit that in memory. The solution to that is hashing. And SciPylearn has an excellent existing implementation of a hashing vectorizer. And this is the code that I used to extract those byte engrams from the files that I was given. So there's a bunch of parameters here. As you can see, I only used engrams from 1 to 3, and that was through a grid search of the parameters and then cross-validation to find out what worked the best. There's a bunch of parameters in here that were kind of chosen that way. So not only is this code showing the vectorizer that I used, but there's that pipeline there that kind of shows extracting into my feature space and then removing features that didn't appear in any of the samples, applying term frequency and inverse document frequency transformer, and then selecting the 500 best features. So you can see that in my pipeline, I kind of had a custom extractor there. Scikit-learn has a great API. I love using it. I love the definition of the API. And it's so simple that it makes it easy for you to extend it through your own custom classes. And I did that here. I did that so that I could parallelize the reading and the processing of all these text files that I had, all these bytes text files. A lot of the processing might have been disk intensive, so I'm not sure how much I gained by multi-processing all this. But I think it's just a testament to Scikit-learn's extensibility and how easy it was to throw this together so that I could run this feature extract function on all of my text files. Last year, I talked a little bit about how PySpark and how I was using that. I kind of got addicted to like linear expressions of data flows there in like kind of a functional style. And so I was kind of looking around for a library that would allow me to do that without using Spark, and I landed on tools, and I've enjoyed using that so far. So that's how I extract them, and that's how I get the 500 best byte engram features. So now I'm going to show you some images that might motivate why those byte engrams are actually useful for classification. I mean, they're pretty low-level features, and it was kind of surprising to me coming across this area, you know, of malware classification that these would actually be useful. So I used a tool called BinGlide here. It's written in Python, and these images are just from that GitHub project page, the introduction, the README file. And these are just some examples. So what you see in each of these images on the left is it's a strip of the whole data that's in an example binary, and those strips on the left show the entropy. And that allows you to kind of like select what parts of the file you're interested in. The part on the right is a 2D histogram of the byte 2 grams. So on the x-axis, we have 256 possible bytes. On the y-axis, we have the same thing. And when one byte follows another, that pixel in this 2D histogram here is lit up a little bit more. And so when you run that on example x86 bytecode, you see, you know, this pattern kind of shows itself, and it's a lot different than if you run it on compressed data, for example, JPEG. Since the in compressed data, you're trying to use as much of the information as possible without taking up the most space. It kind of spreads itself out along this 2D histogram. So those were some examples from the tool. I ran it on a sample here from the competition. This is some data from the text section of that sample, and you can see it kind of mimics the x86 example, the x86 bytecode from the example from the previous slide. But then when you look at the .data section here, you can see a distinct pattern that probably doesn't reveal itself in other samples, and you would hope that any classification algorithm would see that distinct pattern and recognize it and be able to classify on it. So I did the same sort of thing using the instructions from the disassembly file. I wrote some code to rip out these instructions and dump them to their own text file. And then once again, I can count up the number of times each instruction occurs and the different number of engrams. I used similar code to do that. And again, these are the parameters that I landed on. I investigated instruction engrams up to 4, but I got the best results by only using 1 and 2 grams. And I also had a much expanded feature space, hashing space. So a little bit, if you recall the data flow that I had for my final model, named features were kind of lumped into instruction engrams, and that was kind of a result of how I was investigating things. It was kind of awkward. They probably shouldn't have been feature selected along with the instruction engrams, but that's the way it ended up. So these named features are really just categorical variables. They're features that are 0 or 1 if a section name showed up or if a library was imported or not. And so I extracted those with regular expressions from the disassembly files. For each named feature that I was interested in, for example, section names or imports, I just defined a regular expression that matched, and then a function that could take that match from the regular expression library and extract the string that I was interested in. And then optionally, I had a filter that was there if I needed to change the string in any way. So yeah, once I've defined all those regular expressions, then I could just use the same function to extract all the different named features. And again, like you can see, I'm maybe too much addicted to my functional programming here and wasted a lot of time trying to refactor things into this, but it looks real pretty. Yeah, once I've extracted those named features, then I can look at some statistics. These are the top occurring imports in the data set. Those are the top libraries that were most imported, and then the most imported functions. One last bunch of features that I used were manual features. So these were just quantitative numbers that I could come up with that I could. This was really just a brainstorming session. I just calculated some numbers about every sample and threw them into this data structure and included them as features. And these were kind of included next to the 500 best byte engrams and the 500 best instruction engrams. So once I did all that, then I had about 1,026 features, and my final model was based on a gradient boosting classifier from scikit-learn with those parameters, which were again chosen through grid searching and cross-validation. I also tried some other different models, but got the best results from what you see there, the gradient boosting classifier. So this is a TSE Plot that I threw together on my final feature set. When I have 1,000 different features, that's a high-dimensional space that all of my samples live in, and they all have a different distance to each other. And so what the TSE tries to do is to maintain that distance between each of the malware samples in that expanded feature space and compress it into 2 dimensions while maintaining that distance. So you can see that here, and this just kind of gave me a little bit of intuition about what classes were easily separable by the final random forest model and which ones might overlap with each other. And this is the code in scikit-learn that allowed me to make that plot, or make that model that was then plotted in matplotlib. So that was the model. How did I do? Well, I did pretty well. I got 29th out of like 400 competitors, but I'm critical on myself. I'm competitive. I say I did okay. I mean, this is my job. Maybe I should have done a lot better. So my excuse is that I was more focused on productization and learning and figuring out how I can get all of this into an eventual endgame product. And part of that was learning from all the winning teams. The top 3 solutions were open sourced, and these are some of the strategies that those winning teams used. Extraboost is an open source implementation of that same model that I used in scikit-learn. It does have good Python bindings, and I think a lot of the teams in the competition found that it gave better performance. And then the rest of those listed under usable in a product are other features that maybe I could have used. Malware as an image, the compression ratio, and other things. The last 2 are kind of strategies that were only useful in this competition, in that teams calibrated their final probabilities to exactly minimize the log loss, which was the metric that the competition was judged on. Semi-supervised learning was some of the teams were able to learn a little bit from the test set and incorporate that into their models. So on the theme of generalizing into a product, the problem with IDA I mentioned it was a little bit, it's restrictively licensed. It can't really be run in a distributable sense. And so I went searching for a way to recreate those instruction and those instruction engrams. And I came across Capstone, which is a popular open source disassembler. And Capstone has great Python bindings. You can see in just a little bit of code, I was able to extract all kinds of instructions. And most of that code is actually just changing my text file that shows all the data in hex into a Python bytes object. But I extracted all those instructions. I put them right next to the IDA instructions, and I built a machine learning model based only on those instructions. And I evaluated how well they classified. And you can see that's the log loss right there under the mean line. And so the model based on the IDA just had a much smaller log loss, and it was much better. And I think the reason for that, after consulting a couple experts in the company, was that IDA has a lot of analysis passes that it does over the file to determine where functions begin and end, what data is what, and so they do a much better job at producing great disassembly. And Capstone just does a single pass over the whole file. It just disassembles data as you feed it to it. And so that's why it probably doesn't, the features extracted using Capstone don't have as much classification power. So these are some Python projects that do disassembly and include analysis passes that I'm going to be trying to investigate and look into using in the future. And here are some other projects, again, in Python that I have used to investigate malware. PE file is very popular, and it just extracts general information. And there's links to the other ones in that gist I talked about. There's the link to it right there. And those are my conclusions, and I should wrap up. All right, thanks. So I can take questions. No questions. I confused everyone. Okay.
So, hello? I was wondering, I don't do machine learning so much, but this looks like a really complex workflow. Kind of the fundamental understandings of what's going on there are kind of hard to follow, I think, for a non-expert.
Mm-hmm.
How iterative was this as a process to come up with your result there?
How difficult of a process?
How iterative was that?
How iterative?
And as follow-up to that question, kind of how helpful is the SciPy community in providing those tools for you to iterate quickly?
That's why I'm here, is that the SciPy tools were very helpful, and I had been using them in academia, and now I'm using them, while I work in this security company, and it wouldn't be possible without them. Yeah, my talk was more of like this is a view from the trenches in a commercial enterprise using these SciPy tools. But then how iterative was the process? It was very iterative, maybe not enough. Like I mentioned that kind of mistake that features probably shouldn't have been included together. But in coming up with this, I was more like exploring the features that you can extract from malware and trying to understand them. And I was kind of less focused on getting the best pipeline for the best classification, because I figured, the best strategies would be open sourced, and then I'd be able to learn from those as well.
So I used to use IDA quite a bit in the past. I'm kind of curious if you think that we should be building tooling to like build the next version of IDA but open source, to piece together some of these, but where you get kind of like a rich environment that's specifically for disassembly and interaction with like those same data structures and overall database that IDA gives you.
I mean, I think I would have benefited from an open source tool that disassembles as well as IDA but I mean, there's a lot of IP that goes into IDA and like, you know, I think it's the best for a reason, and because people pay a good amount of money for it. And so yeah, I would love an open source tool that would give me disassembly, but I understand why it doesn't exist, or why it might not exist. I still need to go looking for it. And I think there was one other question.
So this is really cool. And I was wondering if you looked into basically the same sort of classification, except for vulnerability detection rather than malware.
So the question is using the same sort of techniques for vulnerability detection. I haven't looked into that yet, but whenever approaching a problem like that, I'd ask, you know, what is the data? What can I use to process? And that's one of the problems in the security industry, that not all our data is labeled, and it's kind of it's a time-consuming and a by-hand process of labeling the data. And so that's the first kind of questions I'd ask when confronted with a new problem in the security field that might be solved by machine learning or data science. Okay, thanks.